Okay, so now it's 3:30 in Germany and unofficial DVCon time. So let's start with the afternoon session. So we have three interesting presentations, and the first one is given by Antonio Genoff from NXP. So Antonio, please start with your presentation.
Thank you, Tilo. Hello, everyone. My name is Antonio, and I'm a PhD student at NXP Sophia Antipolis in France. And today I will talk about power. So I will present you a power estimation methodology that can be applied at the very first stages of the design flow. And I will give you our first evaluation bench that we have created. But before that, I would like to introduce part of my motivations to do whatever I do. So yeah, in in our busy daily lives, the average person spends really a lot of time behind the wheel. That's why the engineering industry is doing everything it can to make us feel at home in our vehicles. So today's in-car media system entertainments are so varied and high performance that you can always find something to do while driving. You've got a lot of features at your disposal, like call answering, streaming music, weather forecast, connected navigation systems, Netflix pre-installed movies, popcorn machines, and more and more. Not to mention all the boring stuff that keeps the vehicle safe on the road. But yeah, all those above mentioned systems consumes energy, and in a modern vehicle, they are really a lot. As we know, batteries have limitations such as capacities, physical dimensions, weight, and cost. And any watt used for infotainment cannot be used for something more critical than that. Therefore, the autonomy and the power management of the devices are very important. That's one of the reasons why engineering are working hard to create energy efficient systems, and one of the reasons why I work on this subject. Like I said, the power consumption is really a key topic nowadays. It is a major cause for circuit design respins due to limited power budget, glitches, or suboptimal power intent caught too late in the design flow. We are already in a highly power-aware designing era, and the most modern area of development, such as 5G, IoT, and automotive, are based on high performance and low power designs, which is great. But can we really continue to ensure the low power with all this added complexity and device performance in long term? I'm not really sure. So yeah, however, the point of all this is that we should do something to simplify the study of power consumption during the design flow. The biggest gap here comes at the very beginning of the flow. At early stage of architecture definition, we have only a rough idea about what power consumption can be. So at this stage, architects are swapping between specifications, calculation, manufacturers' documentations, tables, and Excel sheets, etc. So there are not too many automated tools or PhD students that can help architects in this struggle. At this stage, the power waste can be considerably reduced thanks to the right choice of components, and that is not obvious without simulation-based verification. In my opinion, the way to achieve this is to use the goodies that we already have and to try to abstract them to a level that allows us to easily understand them. Thus, we fixed as a goal to find a way to estimate the performance and power consumption of a given chip as quickly as possible without too much effort and without breaking something on the road. And in the best case, we want to automate it and make it work for complex use cases on different platforms. The first reason to do this is because we need to enrich the static datasheet Excel approach with a dynamic one, increasing the capabilities of architectural exploration. The dynamic simulation-based verification can allow us to study different architecture options early in the design flow and to optimize the trade-off between power and performance. If we want to go even further than that, the extracted metrics at the beginning of the flow can be used as a reference by designers and developers that will follow our specification. And if you are extremely good, we can even avoid certain bugs and reduce the number of design iterations. In our solution, we use the well-known SystemC TLM library for the functional IP modeling. TLM 2.0 is to abstract the communication between IPs while considering the timing and protocols. And for the power estimation, we use a library called PwClkARCH, which is currently the mystery in this presentation that I will reveal. PwClkARCH is a C++ SystemC library developed for ESL power estimation. Most of the semantics in this library are based on the UPF standard and are abstracted to the TLM level. It includes components such as design elements, power state tables, power switches, and supply nets. Considering that there is no current standard for a clock tree description, so PwClkARCH introduced a methodology that allows the insertion of external clocks, generated clocks, DPLLs, clock managers, and the clock state table, which is similar to the UPF power state table. Power and clock specifications are built over the design elements to define the power intent. In this way, the separation between hardware design and power clock intent is reinforced. The power intent definition and the use of operating performance point table enable us to define power management strategies such as clock gating, power gating, DVS, DVFS, etc. In all this at the architecture level well before the RTL is available. There are several key points about this library. PwClkARCH allows us to maintain the separation between the functional model and the power intent. This means that there is no intrusive power-related code inside the functional model, allowing it to be reused for performance estimation or just making it more readable and efficient. It also allows parallel simulation between the functional and power models. We can observe the influence of each power management strategy on the performance of the functional model, and we can find the area of improvement in power management of a device, for example. The PwClkARCH library is able to continuously track the power consumption of all IPs in any architecture running any application. Of course, it is not the first solution to try to fill this important gap in the design flow. There are several academic and industrial solutions, but they do not provide us with all the semantics and mechanisms that PwClkARCH can provide. Some of them are based on static approaches that require a great deal of human effort. Others do not allow the use of power reduction techniques, or at least not outside of the functional model. The majority is based on power state machines where we manually associate power consumptions to each state, and they may require a lower level of abstraction. PwClkARCH uses a different approach. This library does not use state machines, but relatively precise information on the surface and the activity of IPs. The consumption is extracted from the sum of this information and is considered to be more accurate than the power state based one. Here is a simple example on how we define and use these semantics. In the first snippet of code, we create the clock domains by simple instantiations. Then, in the same way, in the second snippet, we instantiate power domains. Once that is done, we can start creating the design elements like in the third snippet of code, and each IP under test will have to be associated with a design element. Design elements are the ones that will compute the power equations for their corresponding IPs. Therefore, when we instantiate them, we need to provide the clock domain, the power domain, a pointer to the IP functional model, the IP capacitance, and leakage resistance, and if necessary, an initial activity factor in the range between 0 and 1. The implementation of the additional components such as DPLLs and power switches is as simple as the components presented above and is given in the snippets 4 and 5. Once the power intent is defined, we are ready to move on the implementation of the state tables. Here's a simple example of power state and clock state tables and an operating performance point table. The power state table contains the supply nets, including the switched ones as columns, and the added states as rows. The clock state table contains the source clock input to the design element that takes as value a frequency divider and all clock states defined by the architect. The OPP table contains a multiplier and a divider for the DPLL of each clock domain, and the last column of the OPP table contains the position of a given power state and clock state pair extracted from the power state and clock state tables. At the end, we create the power management unit module and pass all these tables to it as arguments, allowing it to create the clock managers, GPLL controllers, and to establish all the necessary connections. So that was a simple overview of the main functionalities of PwClkARCH. The SoC under test in our study is the NXP IMX8 QuadMax, which is part of the IMX8 family. Each device in this family follows a similar structure. They all use a switch matrix to establish the communication between all the subsystems. A block called SCU, or System Control Unit, is responsible for the reset, clock, and power management. In our platform, PwClkARCH PMU plays this role. And finally, we have one or two external DRAM memories, so one or two DRAM controllers called DRCs. We can have a large number of subsystems connected to this interconnect. For our SystemC test bench, we have developed some configurable generic traffic generators and some application-specific ones in order to generate the stimuli. We have used simple and configurable DRAM models for the memory access modeling. And we have developed a detailed timing-aware functional model of our design under test. As you can already guess, our design under test is the switch matrix. This is a large and complex module which contain many sub-blocks and has a high granularity. The main feature of this module are the programmable course interleaving, the system address decoding, transaction routing to the memory mapped SoC components via cross-linked NIC fabrics, and in addition, quality of service algorithms are applied in this module to manage the scheduling and the reordering of transactions according to their priority. The QoS traffic arbitration is performed at several levels. We have described the power intent of our DUT using the previously mentioned methodology, and it contains about 1 voltage domain, 5 power domains, and more than 25 clock domains with hardware auto-clock gating enabled. The simple multitask use case presented in this paper is divided into 4 main phases. The first phase is a full activity phase where all traffic generators are activated, and therefore all switch matrix blocks are switched on. The transactions are aimed at the 2 memories, so both DRAM controllers are also active. Then we have an idle phase where we stop all traffic generators and we verify the operation of hardware automatic clock gating. The third phase starts only the half of the traffic generators which normally activate approximately a half of the switch matrix blocks. The traffic here is generated in such a way that it only accesses one memory at a time and interleave between the two memories. And the fourth and last phase is the power down phase. Here we apply the power gating on both DRAM controllers, and we scale the voltage for the switch matrix, switching it to a low power mode. Here is a total power consumption curve for this given use case. And here the four phases can be clearly observed. We have the maximum power consumption during the first phase because everything is active. Then in the second short phase, we see that when the traffic is over, all clocks are gated, including the DRAM controllers, and only the static power consumption remains. During the third phase, the power consumption is almost halved because the biggest power consumer is the memory module. And here we have only one active memory at a time. Of course, there is also the fact that only half of the switch matrix clock domains are activated after the phase 2. The consumption peaks come from the interleaving between the two memories, which is the only time when both memories are activated simultaneously during this phase. At the end, in the fourth phase, we first see the clock gating of all blocks, and after a short period of time, when all processing is finished, the power gating is applied. This slide is only to illustrate some more metrics extracted from PwClkARCH. We can extract separately the static and dynamic power per power domain, per clock domain, and even per design element, which means per IP. We can also observe the clock activity of each IP and check the clock gating mechanism and frequency scaling if we have one. We can also extract the overall energy consumed during the given use case. Here again, we can clearly check all the previous observations. During the third phase, the slope is high and linear because everything is active and consumes energy. The second short phase, there is no more activity, so no more energy consumption except the static one. During the third phase, the activity is lower, therefore the slope is lower than in phase 1. And in the fourth phase, there is nothing except the static activity. Here's a general conclusion with the correlation between our simulation and similar use case measurements on silicon. As we can see, we have a pretty good simulation precision, turning between 90–98% with simple use cases like this one. Here, the correlation was made with real silicon measurements because we are working on a chip that already exists. So yeah, based on the initial assessment and the result obtained, we are convinced that this technology is very promising, and we are constantly testing it and exchanging with its owner to improve it and simplify its integration in the design flow. It can be very interesting to integrate this technology into an industrialized EDA, which contains SystemC functional models library with the most popular technologies, and allows the inclusion of third-party models, of course. In this way, it will not be necessary to develop functional models for complex systems such as LPDDRs, ARM processor, or GPUs. For information, we continued our study and presented a second paper to DVCon, which is presented by Amal Ben-Amer. This paper is based on the same platform and contains some additional use case simulations, plus the co-simulation between PwClkARCH and the open source memory estimator DRAM Power. I believe that it is just the next presentation, so do not hesitate to stay for it too. Thank you for your attention. I hope you enjoyed my presentation and that I successfully transmitted my passion at work. Do not hesitate to throw me your questions or feedbacks, and I will be really glad to accept them and try to answer them. Thank you.
Okay. Okay, thank you, Antonio, for your presentation. So normally you would get now a big round of applause. So yep, thank you again. So are there questions? I noticed that there have been a question in the chat which has already partly been answered, but still maybe Jakob, not sure whether you can unmute yourself and ask the question, or I can ask you to unmute. Or I'm not sure whether we can hear you. So the question from Jakob was, how is it different from the Dokia tool, which was built in Grenoble some years ago?
Dossier tool. Yeah.
Dossier, yeah.
Yeah, it's a great question. Normally in the paper we have made a comparison between the two. So Dossier do not have advantages and disadvantages. Dossier allow us to create power reduction techniques and to apply them, but they are not really simulated in parallel with the functional model. So what we do, what is done in Dossier, in fact, is to create a CSV file containing some functional events and simulate it with another power estimation tool, if I'm not wrong. And that's a separation between the functional and the power model. Advantage of Dossier is that they include the temperature in their measurements.
Okay, so there have been two additional questions, so which both relate to software. So the question from Lukas Jünger was, could you talk a bit more about the software you executed on your platform? So
yes, for now, our design under test is an interconnect. So what we are interested to have is just the traffic that will pass through that interconnect. And what we do is to generate some read-write transactions in with different delays, different orders in order to simulate the platform. With those, we did that with the generic traffic generators. And for example, that can represent a memory copy for this use case. In the next paper that we will presented by Amal, you will see more complex use cases like display refresh and in the mem copy. Just to answer really the question, yep. We do not turn on OS on the platform. We do not use emulators or ESS. We are just generating transactions. And I see the additional question. No, it is not blocking transport. It is non-blocking. So because we need to have information about the timing.
Okay. Yep. So one question from my side, you were talking about integration into EDA tools. So is your library open source available, or how do you envision from EDA companies some integration?
Yeah, the tool is not open source. we use it in NXP in collaboration between us and LIAT Laboratory, which is based here in Sofia Antipolis in France, and who created this library. And to integrate it in an industrialized UDA, they are searching for collaborations with vendors.
Yep, interesting to know for the EDA vendors too.
Yeah,
maybe reach out. Okay. There has been another question from Jakob.
Yeah,
Whether
I see it. I see it. Yes, we look for the activity levels in the IP. Though we can easily add different activity stations. That is really easy with the PwClkARCH library. We just need to add one more method or two. That it depends how we want to apply it, and we can change the activity factor for each design element for each calculation. It is taken in account in the power formula, power equations.
And there's been a question from Martin whether you have looked into IEEE 2416 regarding power modeling and whether there's some relationship.
I'm not sure if that corresponds to UPF 3.0. Maybe I don't know.
Yep.
If it's that, we have already looked, and our approach is based on this one, but we have abstracted it to a C++ TLM kind of code, and it's less verbose, and also it includes a clock management definition, which is not included in the UPF 3.0, and which is very important, I believe, for the power.
Okay, so I think we are also from time point. If there are, there's another question. How much slower are you compared to a loosely timed coupled TLM model?
It is a good question, but in our approach, we directly started with the approximately timed, because we needed the timing information, and we did not develop the LT model. So I can't really make the comparison, but I don't believe that there is a great difference in that case.
Okay, so then just a quick follow-up from my side regarding this question. Do you have a big overhead when you enable your power measurements on your model?
No. The simulating the functional model and the power together and outside of the power model, it takes maybe the same time. I don't think that that include more complexity or simulation time.
Okay, so yeah, thank you again for your presentation, Antonio. And now I will ask Amal to share his screen. So yep.
Just I will stop sharing.
Yep. So maybe you can stop sharing, and we will wait maybe for 1 minute till it's exactly 4 o'clock, so that others can join.